Thank you, the organizers, for inviting me. Thank you for the presentation, Jason and Seba, sorry. It's a really great opportunity for me being here and explaining you these results. It's an honor also being the last one. You probably were expecting a professor and Nobel laureate, but this is what you got. I'm going to present you today some, hopefully for you, nice results on Yttrium Iron Garnet that we have been coupling with niobium and bismuth and copper, trying to induce, if possible, Zeeman splitting, superconductor, or inverse spin Hall effect, or spin Hall effect on these materials. So first of all, let's thank Jason again for leading all this group, Angelo Di Bernardo, who just told me everything I know about PLD, and Lauren Mackenzie-Sell, which is our FMR person in-house. So the motivation is pretty simple. I will show you how we start growing these materials by pulverized deposition, and then how we've been coupling with niobium and the results we observed with ferromagnetic resonance, and just last but not least, bismuth YIG and bismuth dope copper YIG. The motivation has been explained thoroughly from the whole conference. Suggests you know that in spintronics, in a normal metal, ferromagnetic metal, you can get a spin polarized current at the end, but it's still not energetically or efficiently. It's not really efficient energetically. If you are able to couple the superconductors and a ferromagnet, which are, of course, believed to be incompatible, you could have these quasi-particle excitations at the end being spin polarized. That would be the main idea. It's been introduced by Mark, by Kunrock the first day, and also beautiful by Elia yesterday. This is the material we work with. This is the Yttrium Iron Garnet. It's a garnet, so the unit cell is pretty monstrous. So what we have is yttrium, iron, and oxygen with 160 atoms packed in a pseudo-cubic unit cell. So this material is a ferrimagnet, and this ferrimagnetism is coming because these yttrium ions are coordinated with iron ions, which are octahedral and tetrahedral. And these octahedral and tetrahedral sites are giving a different magnetism. At the end, is a ferrimagnetism which is not compensated. So instead of having an antiferromagnet with compensated planes on growth, what we have now is uncompensated planes on the z-axis. It's a pretty nice material for ferromagnetic resonance because the line shape of the magnetic resonance is extraordinarily low. The damping parameter is quite low as well. It's a high Vertex factor material and is extraordinarily insulating. Recently, last week, I think, it appeared a paper on arXiv saying that it's not really an insulator. So it's a semiconductor with extraordinarily large band gap, but we can treat it as an insulator for the time shake. So why we want thin YIG? The YIG can be produced by liquid phase epitaxy. It's quite high quality, it's extraordinarily high quality. But if you want to use a ferromagnetic resonance, thick YIG has many modes, which are on the top of this normal mode at lower thickness, and we cannot use this non-invasive technique to study spin pumping into materials. So this is why we have to go to thinner layers, and they are quite controllable using PLD. So that's just an idea of the PLD that we use. We have, you know, quite good already. What we have is a rotating target of a polycrystalline material, which is YIG. Then a substrate is sitting on a heater, and then with a controlled environment of high purity oxygen and temperature, what we can obtain is a layer by layer deposition of these materials. We know it's layer by layer, even though we have no lead or read in situ. What we can do by growing is characterize it ex situ by, for example, X-ray diffraction, and we can see that sitting on the top of our substrate, which is another lattice match garnet non-magnetic, we can get a really nice film with these clear lower fringes telling us that what we have is a layer by layer growth. Going to the superconductor space map, we see no real large strain on our thin samples. See here we are talking about a 40 nanometer sample thick YIG on the 111 direction, and no traces of roughness in the reciprocal space map. Roughness or stress, we can find it on the reciprocal space map. YIG has to be carefully deposited because you can have extended out of place lattice parameter coming from partial relaxation. So we have to carefully select the samples that shows nice lower fringes and we have we have only relaxed YIG, but not strained YIG. The problem of the substrate that we use, which is the commonly established substrate for YIG, is that the lattice parameter is slightly different, and it can give you elongation of the z-axis out of plane, giving you a tetrahedral more than cubic phase. Then our YIG is as smooth as we can produce. If you just go about 10 by 10 microns AFM, the roughness overall is always lying in something like 0.15 nanometers, which in the terraces is negligible. And we can see that from TM experiments that the crystallinity is quite good. And last but not least, we've observed the most important feature of our YIG, which is magnetic as we expected it to be. Then people has been using YIG. One thing I'm brushing a lot, but anyway. People has been using YIG in the last years because as long as it's an insulator and it's very magnetic, you can use it, for example, to propagate magnons. The propagation of magnons of YIG on platinum on YIG has been observed with local and local experiments. For example, this experiment for Bartman-West in Groningen. These magnons can stand micrometric distances, and not only that, you can also have a different layer on the top of the YIG, for example, graphene, and have these magnons going onto almost millimetric distances. Some other experiments involving YIG are studying the spin transfer torque, which are something more related to what I'm showing you today. For example, this work here with Sebastián Berreyer was involved in San Sebastian, and how, for example, from the study of the Gilbert damping parameter on the ephemeral resonance, it's possible to study the spin transfer from the YIG to a platinum stripe through an insulator layer. The building block for our ferromagnetic resonance YIG for ferromagnetic resonance is the YIG niobium bilayer. And the niobium is deposited by spattering. This is spattering after the PLD. We just pretty much characterize the growth rate and the conditions of the niobium sticking on the YIG. The roughness does not really change dramatically, so we go from 0.15 nanometers to 0.3 or 0.4 nanometers on chip. And the first thing we can observe is that if we have the same samples of YIG and we just deposit different thicknesses of niobium, we have a really depletion of the TC of the niobium when sitting on YIG compared to niobium sitting on silicon dioxide. So we already see that the interface is doing something to this superconductor. We have studied the ferromagnetic resonance both in cavity and strip lines. You know, probably much better than I do, that from the ferromagnetic resonance, what you have here is a perpendicular, you have in-plane magnetic field. You can, from the Kittel relation, establish the magnetization, which is going to give you the idea of the position of the ferromagnetic resonance, which is going to give you an idea of the magnetization. And from the width of this resonance, what you can observe, what you can estimate is the Gilbert damping parameter, which is nothing else but also the capacity that we'll have this material to spin pan electrons to the next layer. The first studies some of the studies that trigger our interest with this old work by in the group of Jan Arts that we have is just if I remember well, it's just permalloy and niobium, and permalloy and niobium from FMR against the magnetic field, and at different temperatures you can extract the spin pumping into the superconductor. This is our typical waveguides. What we just create is a straight line of cold on the top of our niobium YIG or on our YIG, and with this we can study FMR at room temperature and down to 4 Kelvin. Estimating the Gilbert damping parameter of YIG at room temperature is pretty straightforward. So you can use cavity FMR or strip lines, and from the Kittel relation we can estimate the magnetization of our YIG, the digital magnetic ratio, and also from the full width or half maximum of this line, we can obtain alpha parameter. Our bare alpha damping is not bad. So we are talking about from 79 nanometers of YIG, we have something like around 7 10 to the minus 4 alpha. But what we is quite noticeable is that if we have YIG and we characterize our alpha parameter and then we deposit niobium on the top, this alpha damping increases by a factor 5. So we see, or we can start thinking that our niobium will be acting as a spin sink of spin from the YIG. Things have started to get a little bit more complicated. We're going down in temperature. Still, is it possible to follow perfectly the YIG, the FMR of YIG at different temperatures? But there is not really much known about what happens below 10 Kelvin. So YIG's Gilbert damping parameter apparently increases at low temperature and then started to decrease. And this is something that people thought that is coming from 2 magnon scattering and impurity relaxation, but it's still something which is under debate. And this one here, this is the full width of half maximum of the width of the ferromagnetic resonance against the temperature at a given frequency.
May I also ask, do you understand the magnon spectrum of the YIG? I mean, there should be a gap in the magnon spectrum, I guess.
Yes.
And what is the size of the gap? I mean, does it correspond to this temperature?
So the size of the gap of YIG, as it is something like the order of 2 to 3 electrons.
No,
I don't know.
Because if there's a gap, then below this gap, basically you have much decreased line.
Then, if we go slightly lower in temperature and we just study the bay YIG, what we have observed is that the magnetization increases by lowering the temperature, and this has been previously observed in just best samples of this YIG, and it's been reported that there is a deformation blockage and its entropy is always higher than expected at lower temperature, and this gives you a slightly higher effective magnetization per unit volume as the bulk you will expect at room temperature. Then when we couple the niobium to the YIG, when we deposit niobium to the YIG, we had to start studying the FMR by vector analyzer and locking techniques, and also to apply a slightly modulated magnetic field to get all the resonances at the different temperatures, because by going down below the TC of our niobium, that 35 nanometers, something like 7.7 Kelvin, as you can observe here, the resonance was completely hindered in our spectrum. So we had to overcome this problem just by introducing an alternate magnetic field on the top of that, which is modulated, and we could start observing how the Gilbert damping parameter and the full width at half maximum was changing as a function of the magnetic field at different temperatures. So our main results here, which are still ongoing because we have many samples to study and different thicknesses and configuration, is that what we have is that the Gilbert damping parameter is increasing, and at some point close to the TC of niobium, we have a dramatic reduction of this alpha parameter. And this, we have to distinguish this reduction of the alpha parameter if it's coming from the spin sink of niobium or from these 2 magnon scattering. And that's the progresses on what things we are doing now. Now we move to the bismuth YIG and bismuth doped copper YIG. We started thinking also, once now we have YIG, why don't we use it for spin Hall effect measurements? So we got this paper, which is a paper from Fert and Otani, that in 2012 they were studying this giant spin Hall effect in copper bismuth alloys. In these copper bismuth alloys, they would observe that it's a giant spin Hall effect, that it could be as high as 0.24 in angle with 0.5% of impurities. And we wanted to know if it will be possible to induce more impurities of bismuth on copper and then to try to get a higher value for the spin Hall angle. So the first thing we studied, we went to a synchrotron and say, okay, are we able to grow bismuth on YIG, just bismuth on YIG? And the answer is yes. It took us a little bit of time. It was pretty challenging just depositing in situ monolayers of bismuth on YIG. And what we have observed is that it's possible to grow bismuth on YIG, even though the crystallinities and the unit cells are extraordinarily different, which is oriented out of on the z-axis, out of plane. In plane, we probably have a polycrystalline film, out of plane, what we have is a pretty descent-oriented film. So we can grow high-quality bismuth on the jig. We also did some ARPES in Electra, in Electra synchrotron, and we were studying if jig is going to modify dramatically the bismuth, the bismuth states, so the different layers of bismuth at different energies. So what we have observed is that if we just have a cut of the band structure of bismuth on jig, what we have is the polarization of the bands at different energies. And this polarization of the bands was obtained, of course, during ARPES, Argon resolved photo-emission spectroscopy, and they compared pretty well for bare bismuth. So we are able to deposit bare bismuth, which is going to be as good as more or less as good as the crystalline on the top of the jig. So we were ready to study bismuth cobalt. The bismuth cobalt is deposited by Joule evaporation. This is exactly the same evaporator that we used for the previous experiments. So we have to bring all this machine to the synchrotron. We have to calibrate everything every time. And with that, we are able to introduce copper doped with bismuth. So here you have this with the spectra with the copper 111 growing on a sacrificial sample. And you can see that if we induce different, or we start to increase the concentration of bismuth, we also observe the square root of 3 times the square root of 3 reconstruction of bismuth on these samples. We cannot go beyond 10% of bismuth in copper, unfortunately. If we go beyond that, we start to get clustering and segregation of the two phases. So we have observed this on just normalized XRD. So what we have to do is just compare just pure bismuth here, and practically, okay, this is a mistake. This is just pure copper, and we have to lay within this range of 10% of bismuth and copper. After that, we go from this scenario here, that there is only 5% of bismuth and copper, pretty nice and smooth film, to the clustering and segregation of the particles. We also presented some Shannon experiments. So we went to this for the bismuth and copper K edges, and they will confirm that above 10%, we started to have the two phases completely separated. From TM images, we can also see, for example, here, what we have is at 25% of bismuth and copper, we have the segregation of the two phases. So here we have enriched areas of bismuth with depleted regions of bismuth here, but with the 5% on copper, we have set pretty much an homogeneous sample. And also the experiment that are going right now of FMR resonance and inverse spin Hall effect. These are really extraordinary preliminary results just coming at the beginning of this week. We are observing is that what we have just for 1% of bismuth and copper or 4% bismuth and copper is an increase of the alpha damping parameter on the FMR on jig with this alloy in the top, which for the moment is scaling with the concentration of copper. So again, we are having spin sync on the top of our jig, and we have now to explore, move on, and trying to do it at different thicknesses, different compositions, and of course to go to the millikelvin or the Kelvin regime. These are the conclusions. Of course, I rushed a lot, as I was expecting. So we are aiming to get a spin polarized superconductor. We are studying niobium on jig. The niobium on jig has to be a little bit better understood below the TC of niobium, because we have this two magnet scattering process that could hinder some of these applications or the phenomena, and also that we are able to achieve bismuth dope copper with 10% of bismuth on jig, and the low temperature FMR results and the spin Hall effect measurements have been taken now. Thank you for your attention, and have a nice trip back.